Hello everyone, I'm Mohammed, a postdoc researcher at the University of Pennsylvania. I'm going to talk about SharPer, a permissioned blockchain systems that improves scalability using sharding. This work has been done in collaboration with my PhD advisors, Divya Agrawal and Amra Lebadi at University of California, Santa Barbara. In cryptocurrency applications like Bitcoin and Ethereum, anyone can participate without a specific physical identity. Whereas in distributed applications like supply chain and healthcare, participants are known and identified. In the context of blockchain, we call this system permissionless and permissioned blockchains. The focus of this talk is on permissioned blockchain systems. A permissioned blockchain system consists of a set of known, identified entities that might not fully trust each other. Scalability is the ability of a blockchain system to process an increasing number of transactions by adding resources to the system. There are two classes of solutions for scalability: off-chain or layer 2 solutions that are built on top of the main chain by moving a portion of the transactions off the chain. Lightning networks is an example of off-chain solutions. On-chain or layer 1 solutions increase the throughput of the main chain using vertical or horizontal techniques. Sharding is a horizontal technique that partitions the data into multiple shards. These shards are maintained by different subsets of nodes in the network. Sharding is a proven technique to improve scalability of distributed databases. In distributed databases, however, nodes are assumed to be crash-only. In the crash failure model, nodes may fail by stopping and may restart. However, there is no malicious behavior can be happen. Furthermore, cross-shard transactions are processed using a coordinator-based approach, where a single node is assumed to be the coordinator and process such cross-shard transaction. Coordinator-based approach has been used in permission blockchain AHL, where instead of a single node, a committee called a reference committee, consists of Byzantine nodes, plays the role of the coordinator. SharPer has two main goals. First, supporting Byzantine nodes, and second, processing cross-shard transactions without any coordinator. Hence, SharPer requires a smaller number of nodes, and second, it can process cross-shard transactions in parallel. In SharPer, the network is partitioned into clusters of either 2f+1 crash-only or 3f+1 Byzantine nodes. While in blockchain context, nodes are supposed to be Byzantine, SharPer supports crash-only nodes as well for two main reasons. First, from the development point of view, it is pedagogically easier to introduce complex concepts using Byzantine consensus protocols. Second, the techniques and protocols developed in SharPer can be used in any other non-blockchain distributed systems. SharPer sharded data and assigned shards to cluster. Each data shard is replicated on the nodes of a cluster. And finally, the blockchain ledger is not maintained by any node. Each cluster only maintains its own view of the blockchain ledger. In this slide, you can see the SharPer blockchain ledger. Each color presents a cluster or a shard. Intra-shard transactions of different clusters can be processed in parallel. Cross-shard transactions, this gray box, with non-overlapping clusters can also process in parallel. As can be seen, each transaction has a sequence number. And cross-shard transactions have sequence numbers that has multiple parts, each part coming from a shard. Each cluster maintains its own view of the ledger. So cluster P1 or the blue cluster maintains its own view of this ledger that includes its intra-shard transactions like T1, T11, T13, and T14, and the cross-shard transactions that this cluster is involved in, like T12 and T22. SharPer needs to support two types of consensus: intra-shard consensus and cross-shard consensus for intra-shard transactions and cross-shard transactions. Intra-shard consensus is pluggable and depends on the failure model of nodes. If nodes are crash-only, SharPer uses multi-Paxos, and if nodes are Byzantine, SharPer uses PBFD. The cross-shard consensus needs the participation of all involved clusters. The intra-shard consensus for crash-only nodes is multi-Paxos. It's a well-known consensus protocol that needs 2f+1 nodes. It has a linear message complexity, and the quorum size is f+1. For Byzantine nodes and to process intra-shard transactions, SharPer uses PBFD. In PBFD, the number of nodes is 3f+1, and the message complexity is O(n)(2). I'm not going to explain the detail of these two protocols, and will focus on cross-shard consensus protocols of SharPer. Here we have cross-shard consensus with crash-only nodes. We consider two parallel requests because SharPer is able to process non-overlapping cross-shard transactions in parallel. Here we have two clients that they send their request to two different clusters. Cluster P1 and cluster P2 are involved in the first request, and cluster P3 and cluster P4 are involved in the second request. The initiator primary multicasts a propose message to every node of all involved clusters. The propose message includes a sequence number that shows the order of the message in the initiator cluster, cluster P1. All nodes then going to send back an accept message to the primary node, to the initiator primary node. The accept message includes the sequence number that was sent by the primary node, and also a sequence number that shows the order of the message in the involved cluster. The primary of P1 or the primary of P3, basically the primary of the initiator cluster, waits for f+1 matching accept messages from every involved cluster. If it receives that number of accept messages, it sends a commit message that includes both sequence numbers and multicasted to all involved nodes. Nodes going to commit that message to the blockchain. In case of Byzantine nodes, I'm going to show a single request. We have the request, we have the similar propose messages, and then the accept messages are all to all and includes HI and HJ. The sequence number of here, for example, P1 and P2. If we have more clusters, we then have like HI, HJ, HK, and other. For each cluster, for each involved cluster, we need a sequence number. And then each cluster waits for 2f+1 matching accepts messages from every involved clusters. If it receives that, it sends a commit message. And then if it receives 2f+1 matching commit messages from every involved clusters, it commits the request. However, these two graphs present the normal case situation. We need to deal with conflicting messages, where a quorum of matching accept messages from each involved cluster might not be received for different reasons. First, nodes of a cluster might assign different or inconsistent sequence numbers. For example, in this scenario, we have P2 that receives parallel request, parallel propose messages from P1 and P3. So nodes might assign inconsistent sequence numbers because they receive these propose messages in different orders. Second, if there is more than one overlapping cluster between two parallel requests, nodes do not process the second transaction before committing the first transaction to ensure consistency, to ensure that they order in the same order. And it might result in a deadlock situation because cluster A might wait for transaction 1 to be committed, and cluster B might wait for transaction 2 to be committed, and it might result in a deadlock situation. SharPer uses timers to address this situation. In the presence of crash-only nodes, the initiator primary multicasts superpropose messages to the primary nodes of conflicting clusters. It happens when the timer is expired. And by sending superpropose messages to the primary nodes, and since the primary nodes assign sequence number, there is no other conflicts will happen. In case of Byzantine nodes, all nodes of conflicting clusters multicast super accept messages to say that the timer is expired and we need to reorder the message. And to address deadlock situations, in SharPer, nodes try to reach a unique order between deadlock messages. SharPer also introduced two optimized protocols to deal with heavy workloads. Heavy workloads are the workloads where we have many number of cross-chart transactions. In such workloads, the chance of conflicts is high. So only the primary nodes of each cluster assign all sequence number. In those two protocols, the primary node, the initiator primary node, instead of multicasting propose message to every node, sends super propose message to only the primary node of the involved cluster. And only the primary node of the involved cluster assigns sequence number. As a result, no conflicts will occur. However, we need an extra round of intra-cluster message passing, as can be seen here, for both crash-only and Byzantine nodes. In our experiments, we compared SharPer with 3 other systems: active-passive replication, fast agreement, and AHL. In active-passive replication, 2f+1 nodes or 3f+1 nodes, in case of crash-only or Byzantine nodes, are active, and they inform other nodes about the result of consensus. In the fast agreement, like FAB, instead of 3f+1 nodes, 2f+1 nodes achieve consensus. However, instead of three phases of communication, we need 2 phases of communication. So there is a trade-off. We reduce 1 phase of communication. However, we need to increase number of nodes from 3f+1 to 5f+1. And in AHL, in our implementation of AHL, intra-shard transactions are processed like SharPer. However, for cross-shard transaction, we use coordinator-based approach, where a reference committee processes cross-shard transactions. The first figure shows cross-shard transaction in the case of crash-only nodes. We have 4 different scenarios with 0% cross-shard transaction, 20% cross-shard transaction, 80%, and 100% cross-shard transaction. In each scenario, we have 4 clusters of node, and F is assumed to be 1. We report latency and throughput. When there is no cross-shard transaction, the performance of SharPer scales linearly. As can be seen, SharPer is able to process more than 35,000 transactions with less than 100 millisecond latency. By increasing the percentage of cross-shard transaction, SharPer is still shows the best performance among these 4 systems. However, with high percentage of cross-shard transaction, using sharding has no advantage. Because when we have, for example, 100% cross-shard transaction, it means all nodes are involved in every transaction. And as a result, sharding has no advantage. With Byzantine nodes, we can see the similar behavior. With 20%, SharPer has the best performance. However, by increasing the percentage of cross-shard transaction, using sharding has no advantage. Finally, we increase the number of nodes. In case of crash-only nodes, we increase the number of nodes to 15, and in case of Byzantine, we increase the number of nodes to 20. And as can be seen, the overall throughput of SharPer improves semi-linearly. In these 2 scenarios, we have 10% cross-shard transactions. We have more experiments in the paper. As a conclusion, SharPer is a permission blockchain system that improves scalability by clustering the nodes. Nodes of each cluster maintains a data shard and only a view of the blockchain ledger, not the entire ledger. The view of the blockchain ledger is a linear chain, whereas the entire ledger is a DAG structured ledger. SharPer has 2 cross-shard consensus protocols for crash-only and Byzantine nodes. SharPer also has 2 optimized protocols for heavy workloads. The protocols order cross-shard transactions with non-overlapping clusters in parallel. And the throughput of SharPer increases semi-linearly by increasing the number of clusters. Thank you.